Hello guys, let's move on to the part about matrices and vectors. Let me start with vector first. I will probably begin with drawing two axes. I'm just going to call these axes by numbers. So for instance, this axis is number 1 and this axis is number 2. Okay. Now let me draw a vector in here. Let me say that my vector is located at 4 coordinate points along 1 and 3 coordinate points along axis 2. And there it is. That's my vector. Okay, I'm gonna call it U. So you see a vector has a certain length, which is the distance from here to here. That's the length of the vector. In this example, you can figure out the length easily. It's 5. You can use the Pythagoras for that. And it also has a direction. You see the direction of this vector is that way. So a vector has a direction and a length. There is a vector notation that we use, and we always put a bar underneath the name. So whenever I say I have a small letter and there's a bar underneath, I'm meaning vector. So this vector that I plotted in here could be written out as this. Say U is equal to something in the middle of this bracket. Well, we have 2 coordinates, so there are 2 points in here. There are 2 numbers in here. And one of them is the coordinate along axis number 1. And the other one is the component along axis number 1. And the second one is the component of U along axis number 2. Okay. So let's see, the component of U along axis 1 is 4, as we can see here. So I'm going to put 4 in here. And component of U along axis number 2 is 1, 2, 3. There it is. That's how we define our vector. Alright, now matrices. One way to take a look at the matrices is that they are somehow collection of vectors. There are vectors which are appended to one another. That's one way to look at it. Let me write down a matrix as an example of a matrix. Let's say matrix K. And note that for the notation for the matrices is capital letters and 2 bars underneath. Okay. So let's say K is equal to 1 and minus 1. See, this looks like a vector, and now we can have another vector appended to it and write down minus 1 and 1. Okay. Note that I can again call the entries of this matrix as follows. I can have for each one of the columns I can give it a name, which I call it 1 and 2. And for each one of the rows, I can also give it a name 1 and 2. Note that unlike the vector that I could have plotted it here and visualize it, you can't really plot matrices. It doesn't make much sense to plot matrices. Matrices are like operators. They operate on vectors and give you another vector. Okay, let's see how does it work out. Let's say I would like to operate K on U, right? So K times U, and by the way, that's really means operation. So essentially, you multiply K by the vector U. All right. So let me write out everything. 1 minus 1 minus 1 1 times 4 and 3. Okay, so you probably already know. I assume that you know how to multiply a matrix by a vector, but let me do it in a new fashion. Maybe you've never seen it before. So what this matrix multiplication tells me is that take 4 times of the first column and add it to 3 times of the second column. So let me write out this way. It's like 4, this is equal to 4 times the first column plus 3 times the second column. Alright? Now I can figure out what the value would become. The value would be 4 plus minus 3. It ends up to be 1 here. And I will have minus 4 plus positive 3, that's minus 1. And there we have it. If I operate k, on this u, I will end up having the answer such as this. It's going to be a vector. Okay. It turns out that matrices which look like this are generally called the stiffness matrix. Now that you're doing this course analysis of the standard structures, you will see a lot of stiffness matrices around, and you're going to work with them. So I'm not going to explain what they really physically mean. You're going to see them pretty soon. And just like the stiffness matrices, there are a whole lot of other special matrices that people call them by name. I'm going to write some of them down here. They might be useful. They might be useful to know them. First of all, consider this matrix. I'm going to denote it by 0. As the name suggests, it is a 0 matrix. All of its components are 0. By the way, note that I got rid of these numberings, but you know that, for instance, this is the first column, this is second, this is the first row, this is the second row. So a 0 matrix is also an operator, just like K. But whenever it operates on a vector, it gives us a very special answer. Let's take a look at what kind of answer it gives us. So if I operate 0 on U, I will get the answer which is equal to 0 and 0. Okay, so you can multiply 0 by anything and get 0. That's probably not rocket science. The other special matrix is the identity matrix. It is denoted by I. And this is a matrix which has 1s on the diagonal and 0 everywhere else. Okay. If you multiply I by any vector, you will end up getting exactly the same vector, untouched. Okay, so I doesn't change anything. It's like multiplying a number by 1. You will get the same number again. I has the same performance. There is another special matrix which is called, by the way, let me write the names down here. So this is the 0 matrix, this is the identity matrix, and there is another matrix which we're going to call it rotation matrix. Okay, I'm going to show it by R. So R in its general form is like this. It's written like this: cosine of theta minus sine of theta, sine of theta, cosine of theta. Okay, that's what they call it, a rotation matrix. So, by the way, theta is a number in radian, preferably. For instance, let's put theta equals to pi over 4. Okay, so 45 degrees. Let's say we want 45 degrees rotation. Okay, so the value of this matrix will end up to be square root of 2 divided by 2 times 1 minus 1, 1, and 1. I think you can put pi over 4 into here and figure out that, for instance, cosine of pi over 4 is the square root of 2 divided by 2, and so on. Okay. Now, let's let's see what happens if you operate R on a vector. Let me do it. Let me do it right now. Let me write R times U. Let's see what the value would become. I would do the. I wouldn't write down everything. You can do it yourself. Figure out. I'll just write the answer straight away. The answer would be 0.7 and 4.9 down here. Okay, so wait a second. We applied U, which was 4 and 3. We applied R to U, which was 4 and 3, and we got this number. What does it even mean? Let me plot it on our diagram up there. Let me go up here. I'm going to plot 0.7 and 4.9, and probably it would be up here. It's this guy. Okay, probably you can see that it's as if the U bar is rotated 45 degrees counterclockwise. Okay, so that's pretty cool. So this rotation matrix down here, whenever we multiply it by vector, it would give us the rotated version of that vector by the value of theta.